Okay, in this video, we're going to get some more practice into vector fields. We're going to see an example of a real vector field, of a more full vector field, and then we'll also talk about something new that might even be more useful than a vector field. But no spoilers here. We're going to remember what simple harmonic oscillators look like, again introduced in the last section. Suppose we have the second derivative of the position plus the spring constant divided by the mass of the object times its position equals 0. Remember, this comes from Newton's second law, force is mass times acceleration, and also Hooke's law, where the force is equal to negative k times the position. And remember, this is an undamped spring. So there's this mass hanging from a spring, either side to side or up and down, it doesn't matter. And it's just oscillating back and forth. There's no friction, so it's going in periodic motion forever, is this model. Simple, meaning undamped, right? No friction, harmonic oscillator, just going back and forth. All right, and then we set this up as a system. We introduced in the last section, right, that any second order differential equation can be written as a first order system. Specifically, what we have here is that the derivative of position with respect to time, we know that's velocity, and the derivative of velocity with respect to time, well, we looked at this and said that's just going to be equal to negative k divided by m times y. And again, we're going to choose here that m is just going to be equal to k, and that's going to clean this up really nicely. It's just going to be negative y. And if we do that, we get a really nice system. Let's call our position and velocity vector together x, then dx dt is just the velocity, right? The position rate of change is velocity. The velocity rate of change is just negative position. And we can say that's our function, our vector valued function f, applied to our position vector x. And again, as a reminder, x here is going to be the position and the velocity. All right, so lots of notation, right? Seeing all these vectors. And again, if you really want to be using bold for all of these, you can. That is convention. But if you're just writing with a pencil, that becomes more difficult, so we will be using arrows as well. They are interchangeable, but if you're seeing typed things, you're always going to see that bold. Well, always is a strong word. The higher you go in math, the less consistent the notation is. I remember, as a quick side note, trying to do some independent study once for graduate level mathematics. It was like a couple years ago, and it took me so long to just translate all the notation I learned in grad school to the notation that the book had. And in fact, the book had a whole preface explaining the author's notation, because it's different. Because, you know, these math that's been done 300 years ago, we have pretty consistent notation by now. But if you think about more modern research, Jeff over here in Washington is doing this research and using whatever notation makes sense to him. But maybe unbeknownst to Jeff, there's also, Lindsay in Paris or something doing the same thing or something similar, using the notation that makes sense for herself, right? So the more modern we get in math, the less consistent the notation becomes, which is a bummer and definitely makes things hard. But there are very natural reasons for that. So let's take this system of differential equations and let's see what its vector field looks like, shall we? So we're going to do this by hand. Now, this is really great time to pause the video and see if you can create a little vector field by hand. So this is going to be the position over here, and this is going to be the velocity of the mass over here. And we know, okay, the rate of change of the position and the velocity is going to be this vector. So specifically, we can find some different things, right? Just like before, we can say, okay, well, what is this at the point 1, 0? Well, Again, remember this is position, this is velocity. So the vector here, and again, we can write them as column vectors or row vectors. Sometimes you'll see vectors written with angular brackets, like so. Our textbook uses parentheses though, so I'm going to be consistent with that. We can say, okay, v is 0, and negative y is negative 1. So at 1 comma 0, the vector is 0 comma negative 1. And then again, you could keep on going in this fashion. What's the vector at 0 comma negative 1? You do the same thing. The position is 0. The velocity is negative 1, and you get so on. So you find the point 0 comma negative 1, you draw the vector negative 1 comma 0, right? We go left 1, up 0. And what happens if you do that is you're going to get something that looks like this. You could even have things in the middle. And when you have things kind of in the middle, actually I don't want to make... Yeah, this is kind of what it looks like. You're eventually going to get something that looks like this. And you could do things at 2 comma 0, and if again at 0 comma 2, you're going to get something very similar, but now your vectors are going to be much longer. All right, you're going to get some very similar things. And again, we could plot so many of these vectors and get so many different interesting things, but let's use technology. Let's say we plot a whole bunch of these vectors. And again, we're going to notice that the further away from the middle, the bigger these vectors might be. And that makes sense, right? The further this spring gets from the origin, the faster it's going to be moving and the further it's going to be going. If this spring starts off pretty close to neutral, it's not going to be oscillating very wildly. But the further we get away, right, the more it's going to be oscillating. And again, you could calculate all these vectors, and this really is the behavior that you're going to see. There's going to be diagonal vectors all the way here as well. So let's see what the actual vector field looks like if we use technology. Okay. You're going to see that this very quickly gets kind of out of hand. All right, you see that, yeah, we got this kind of circle that's moving pretty small, right? We got small vectors close. And then we have more circles as we get further away with bigger vectors, right? The spring is moving faster and it's going further. And again, as the further we get out, the more and more you see. And you see a bunch of nonsense, right? These vectors are overlapping each other. And that's going to be very common with vector fields because the length of the vector matters, right? The length of the vector shows how fast this change is happening. This is essentially for 1 unit of time. How far are we moving for 1 unit of time where, you know, this is kind of a tangent line in a sense, it's an approximation, but in 1 unit of time, we're really kind of moving as far as the vector is an approximation. So we have a little bit of information about time here, but that makes all the vectors different directions, or sorry, different lengths, and it really can get pretty messy pretty fast. So what we do is we say, what if we ignore time for now? What if we make all these vectors the same length so that we can actually see what's happening? And when we do that, we get what's known as a direction field. And look at the difference between these two graphs. The direction field is the same thing as a vector field. We just say, let's forget about time, let's forget about speed, let's make all of these arrows the same length so that we can just read it. Okay, so we're gonna mostly be working with direction fields in this class. Because even though this thing over here on the left is kind of nice because it shows us the lengths of the vectors, shows us some sense of how fast or slow something is happening, it very quickly, and this is a very nice system, by the way, this is about as nice of a system as it gets, but it still very quickly becomes pretty messy and hard to read. Whereas this over here is much easier to read, and again, we can't really see how fast anything is moving. Similar to a phase line, right? Similar to a phase line, this direction field doesn't really incorporate time at all. But it does tell us where we're going at any specific moment, or at any specific position. Moment has like a time component, right? So that's pretty much it for this. We're going to be using direction fields more than vector fields. And that means we're going to standardize the length of all these arrows, and it makes it a lot more readable. Anyway, that's pretty much it for this video. Let me know if you have any questions, and ta-ta.